Hi guys, welcome to lesson 19.3. So we're going to study about graphs of linear and exponential functions. So a couple things we want to accomplish. We want to be able to relate the general form of the exponential function to exponential growth. So we'll understand how the function relates to exponential growth. And we also want to be able to compare linear growth and exponential growth and see what the similarities and differences are. So join up with me on page 334 and we'll get started. So as always, I want to encourage you to kind of work through the page yourself and then play my version and follow along, fill in anything that was missing or that you need to add to your own thinking. So here it says bacteria populations can grow very quickly. During an experiment involving bacteria, 2 biology students observed that each bacteria cell splits into 2 new cells every hour. This means that the bacteria population doubles every hour. Alex thinks that the population of bacteria is represented by the function f of x equals 2x. His friend Glenda thinks the population growth is represented by the function g of x equals 2 to the x power. Now, don't worry about the f of x or g of x. Those are just two different function names. So Alex's function is y equals 2x, and Glenda's function is y equals 2 to the x power. In each function, x represents the number of hours. So we're going to complete the tables below for each function. So Alex, at the first 0 hour, that would be 1 bacteria. Then after 1 hour, it doubles, so it would be 2. And then it doubles again, so in his function it multiplies by 2. So after 2 hours it multiplies by 2 times 2 would be 4. 3 hours, 3 times 2 would be 6. And 4 hours, 4 times 2 would be 8. So in Alex's function, we're just plugging x in and multiplying it by 2. So 5 times 2 would be 10. In Glenda's function, we're going to be multiplying 2 to the power of x. So 2 to the power of 0, anything to the power of 0, when we plug 0 in for x, will give us 1. Anything to the power of 0 equals 1. You can try it in your calculator, and we can discuss why later if you want to know and you're not already sure. So 2 to the power of 1 is just going to be 2, and we put 2 in for our x power. 2 to the power of 2 will be 4. 2 to the power of 3 will be 8. 2 to the power of 4 is 16, and 2 to the power of 5 is 32. So which table represents the population of the bacteria the biology students are studying? So it's supposed to be doubling every hour. Which one shows doubling every hour? And that would be the g of x table, right? This one. Because this one's doubling at first, it looks like it is, but then after 2 hours it's doing a different thing. So is the function that represents the growth of the bacteria linear or exponential? Well, it's not linear, is it? Because it doesn't have a constant rate of change. It's changing by a different amount every time. So it's exponential because there is a pattern. It's a common ratio. And so it's multiplying by that factor over and over and over and growing exponentially. Now they want us to graph these two functions on a graphing calculator and set the window to show the first quadrant only. And then we're going to describe the graphs of the functions. So here are the two functions, and what we're going to use to graph these two functions is a program on your computer called GeoGebra. So if you haven't already had experience with GeoGebra, I'm going to walk you through it. So on your desktop, find the icon that looks like this and open that program, okay? If you don't see the icon, then in the search bar, on your Windows search bar, start typing in GeoGebra and it will find the program. All right, now on the next slide, I'll show you how to set this up. Now when you open GeoGebra, you're going to get a window that looks like this here. And if you don't, you might need to select the algebra view from a little window that was dropped down, but this should probably be the default. So the first thing we're going to do is down here in the bottom, we're going to input the function that we need. So our first one is f of x equals 2x. So we'll type in f of x equals 2x, and it'll graph it for us. And we'll hit enter so that one's in there. All right, then we'll type another one that's g of x for the other function name, g of x equals 2 to the power of x. And power is a caret, and on mine it's above the 6, so I have to do shift 6. You might have to search on your keyboard to find it. So up arrow x, and it'll graph that one, then we'll hit enter. So there's our two functions on the graph. Now, it said to set our viewing window just to show quadrant 1, so we can just do that. Since you have a touch screen too, we can just drag it so it just shows quadrant 1, but still shows our numbers for us. Another thing you can do that's handy is if you right click on the screen in the white area, then you can make some options appear, and if you pick grid, sometimes it's easier to see exactly where things are crossing and things like that. And you can also just zoom in by dragging your fingers on your touch screen too, and then get it back to show quadrant 1. So there's what those two functions look like on the graph. So now you're supposed to look at your graphs on GeoGebra and sketch the graph to match it. So f of x, it started at 0 and went up 2 every hour. So after 1 hour, it was on 2. And after 2 hours, it was on 4. And after 3 hours, it would be off this graph. So that would have looked about like, whoa, like that. So that's f of x. And then g of x, if you notice, you can look back at your window, but it's crossing at 1. And then after 1 hour, it had 2, crossing the y-axis at 1, and then crossing here at 2. After 2 hours, it had 4. And then it went on up. So it kind of went like this, and then it crossed over this one, and then it crossed back over, and it got steeper and steeper and steeper. Not quite vertical, but steeper and steeper as it went along. So that's g of x, because it's increasing by, it's doubling whatever it was before, so it starts increasing faster. So now we're going to compare them a little bit. For the graph of each function, explain what happens to the y values as x values increase. Well, in either case, as x is increasing, it's going this way. The y values are going up. So it's starting low and going up. So both are increasing in different ways, right? F of x is at a constant rate of 2. And g of x by a factor, right? A common difference, which is a factor, something you multiply by, factor of 2. So then we examine them and compare the values of each function from x equals 0 through x equals 2. So from right here to right here, and we're going to compare them. So g of x starts higher at 1, right? It starts here, whereas the other one starts down at 0. And but then the linear one, f of x, crosses it right here. So after 1 hour, they are equal. Then f of x is greater until they cross again. At 2. So then the curved one's lower for a little while, and then at 2 hours they cross again and g of x is higher. So from 1 to 2 hours, the linear function f of x is actually higher than g of x for a little while. Now we're going to examine the value of both functions for where x is greater than 2. So everything from here on. So if we look at it, go up here and look at it from here on, everything after that, the curved one's crossing back over, and then it's always going to be above the linear one. So g of x is always greater after x is greater than 2. And do you think the function that we named, g of x, in part A will continue to be greater as x continues to increase? So do you think that after that point here, right where they cross here, do you think that the linear one's ever going to cross back over the exponential one and become greater again? Put your thoughts down and give your reasons. Pause this video and put some thoughts down with your reasons, and then play it again and I'll tell you what I think. So I think yes, g of x will always be greater because it increases at a higher and higher rate as we double bigger numbers. F of x just stays constant. At 2 times the value of x. That's the way I'm looking at it. So yours might be a little bit different. But you should say that g of x will always be greater because that line is never going to, now that this curve has crossed back over, it's going to keep going up and up and up and up and up, and this line's going to keep going this way, and they're never going to cross again. So this one's, the curves is always going to be higher than the line after that point. The function f of x equals 2x represents linear growth, and you know why linear growth occurs, because there's a constant rate of change, right? So because the y values increase at a constant rate over time. The function g of x equals 2 to the x power represents exponential growth, since the y values increase exponentially. So the amount of increases keeps increasing because you are doing timesing 2 to a higher and higher number every time. So describe how the population values change from 1 hour to another for each function. F of x goes up by 2 every hour, right? It's just 2 times whatever number. So it's 1, then it's 2, then it's 4, then it's 6, and then it's 8. Okay, goes up by 2 every hour because you just 2 times the number of hours. G of x doubles every hour. So whatever you had before, you're going to multiply it by 2, so it's going to multiply by a bigger and bigger number every time. What are the slope and y-intercept of f of x? Well, f of x equals 2x. And if we look at that in y equals mx plus b form, this would be our m right there. So that means that the slope is 2, and our b right here is invisible, right? It says, that doesn't say plus anything, plus nothing. So that must be plus 0. So that means that our y-intercept must be 0 because there was no b value there. That is stuff you want to remember from when you studied slope-intercept form. You want to be able to still pull from that knowledge when you're analyzing equations so that you'll be able to graph things that you already recognize. So now we're going to go back to look at that form a times b to the x. Okay, so because the function g of x equals 2x is an exponential function, it has the form a times b to the x power. What are the values of a and b for this particular function? Okay, remember it's in the form a times b to the x power. So try to answer it yourself. And now I'll tell you that the thing to the x power is 2, so that's your b value. B equals 2 because that's to the x power, right? Now it's supposed to be timesing by an a in front of it, and there's nothing there. So a must be, what number do you multiply by that doesn't change anything? That could be invisible. That would have to be 1. So a is 1 and b is 2. What information do these values give about the graph and the population growth? So this tells you that the graph starts at 1 bacteria, right? And that would be the y-intercept. So the y-intercept equals 1. So at 0 hours, when you first start, there's 1 bacteria. Now B is the growth factor. Or the common ratio is a term we learned before when we were talking about geometric sequences. But that growth factor tells you what you're going to multiply by every time. So that tells us the population is doubling because it's got a growth factor of 2. So we want to talk about now on number 9, which function is increasing faster. And when we explain ourselves, we want to use the graph and the tables. So when you're talking about increasing or decreasing, you're looking at the output. So the y values, or your f of x, your g of x. So these are increasing like this, 0, 2, 4, 6, 8, 10. And g of x is doing 1, 2, 4, 8, 16, 32. So g of x is increasing faster. And the table shows the outputs increasing faster than the other function. The graph shows g of x being steeper than f of x, which means it's increasing faster. So again, those don't have to be my exact words, but you put it in your own words and make sure that you're covering the main points and that you understand, that you're explaining your own thinking. All right, so let's see here. You should try these two by yourself and then play it and see what I thought, okay? So it's much more interesting what you thought because you're the one learning this and forming some new thoughts. That's much more interesting than someone who already knows. So for number 10, we're supposed to describe the graphs of these two functions, f of x and g of x. So I would say a couple things, I guess. F of x is linear with a y-intercept of 0 and a slope of 3. And then g of x is exponential with a y-intercept of 1 because I can't see that a value, right? So it must be a 1. And a growth factor of 3 because that's what's getting to the power of x. And then for number 11, we're going to graph them on a graphing calculator and see what happens to the values of each function as the x values decrease. So describe any differences in how the values change in the two functions. So you should go do it yourself on a graphing calculator. I won't walk you through that this time. Okay, you can look back at how I did the other ones if you need to. And then decide what happens to the values of each function as x values increase. In both of these cases, as x increases, the y's also increase. They'll both be going up. F of x goes up exactly 3 each time. And g of x goes up by tripling, right? Multiplying by 3 each time. So make sure that's what your graphs look like and that you could pull that information from the graph, that you could see those things happening. And you'll come up with the words better and better the more you practice. So the more you've got to practice putting some thoughts down before you listen to me, and then we can always add to your thoughts or revise them if we need to. I just realized what I might need to tell you is how to get rid of these old ones. If you click on the function over here under function and then hit delete, it'll go away. So you can delete them that way. Click on it, delete it, and then you can put your new ones in. So like f of x equals 3x, enter. And then g of x equals 3 to the power of x, enter. And then you can zoom in and look at things if you want to do that. All right, so we have a little disagreement here. Alex believes that for the linear function f of x equals 50x and the exponential function g of x equals 2 to the x power, the value of the f function is always greater than the value of the g function. Glenda believes that for a linear function, f of x to always be greater than an exponential function, the graph of the linear function must be very steep, while the graph of g of x, the exponential function, must be very flat. She proposes graphing f of x equals 50x and g of x equals 1.1x to test her conjecture. So first we're going to test Alex's conjecture by graphing his two functions on your graphing calculator and seeing if you agree with him. So go ahead and do that. Set that up on yours and see if you agree. Is the linear function, this is what Alex thinks, the linear function is always greater than the exponential in that case. So go see what you think. So let's see, he had f of x equals, you can double click it and edit it if you want to, or you can delete it and start over. F of x equals 50x, oops, didn't get me. 50x, got to hit enter for it to save that, and then g of x equals 2 to the power of x. All right, so let's see. Is it always greater? It looks like it is. We might have to zoom out pretty far to see what it does way up there. Ah, look at that. Look what happens. Do you see where the red one passed the blue one though? So if we get high enough, that exponential one is going to actually be higher than the linear one. But we couldn't tell that at first. So I would not agree with Alex, and I would explain that if you put your x values high enough that you would eventually, that exponential function would pass the linear function eventually. Now it wants us to adjust our viewing window to match the coordinate plane shown. So we're going to have to actually change the values on the x and y axis in GeoGebra, and I'll show you how to do that now. All right, to sort of change the X and Y axis, we're going to have to come over here to this gear over here on the right side over here, and we're going to have to pick this setting. So pick the gear and then pick graphics, and that's going to let us make some changes about our X and Y axis. So first of all, go on the grid tab and change, let's see here. Let's go to basic. Let's change our X minimum to be 0, if you look at the picture they want you to do, and make the maximum be 10. And for the Y minimum, we're going to go 0, and it goes all the way up to 500. So let's take a look at that and see if that gets us what we need to see. And then I'm going to look at grid here just real quick and see. Yeah, it's going to go by 0.5 and 50, so that looks good. All right, so then if we zoom out, it's not quite right because they don't have the in-between lines, but we've got the same scale going from 0 to 500 and 0 to 10 and a little beyond. We just don't have all the in-between half lines that they have also. So this should be enough to get us started, and we can see what's happening where these two are crossing at just about a little bit before 9, and this one goes up by exactly 50 each time. So let's sketch that on our graph. So the f of x graph starts at 0 and it goes up by 50. Every 1 hour it goes up by 50. So 2 hours would be 100. So it keeps going like this, exactly up 50 every time, which is what's making it be linear. And the other one starts off at 1, so it's very, very close to 0, and it curves up by tripling, and somewhere, just before 9 is where it actually crosses over. So that would be the g of x function. So let's try to get these as close to accurate as you can without making yourself go crazy about it. You want to make sure things like starting places and intersections are as close to accurate as possible. So adjusting that viewing window really gave us something better to be able to talk to Alex about. So the question here is, should he revise his conjecture? We'll use the graph we just created, and we'll say yes. If you look at the function just before x equals 9, the g of x crosses over and is greater than, that's a t, f of x equals 50x. And he thought that 50x was always going to be higher. But ultimately, exponential function will always pass a linear function. So it's up around output of, like 425 or something like that, where it's becoming higher there. Somewhere around x equals almost 9 and right about 420 something. All right, so now we want to test Glenda's conjecture by graphing these two functions. So I'm going to let you go ahead and go do that by yourself now. You know what you're doing. And then we're going to see if we agree with Glenda. And her conjecture was that this, in order for a linear function to always be higher, the exponential function would have to be really, really flat. So she chose a smaller growth factor to see if she could make sure that the linear function always stays higher. So see if she's right that the linear function always stays higher or not. So hopefully you were able to successfully change your scale and viewing window to match the one they wanted you to match so that you could sketch it. Here's what mine looked like. So still, it looks like that linear function is higher for a lot longer, but still at some point, maybe around 87 or so, that exponential one actually passes it, somewhere above 4,000. So it's still, exponential function eventually became higher. So do we think she should revise her conjecture? Yes, she needs to revise it, and we can use our graph to support us. If we widen the viewing window enough, we see, if we widen it enough, we see that 1.1 to the x power still passes over 50x. So this was the f of x function. This was the g of x function. Is an exponential function always greater than a linear function? No, the linear functions were greater at first. The linear function might start off higher. But eventually, an exponential function will always pass it. So it's not always higher. So this function here, f of x, is higher all the way up until output's above 4,000, right? When x is something like 80 something, right? So it's not always that the exponential is higher. It's just that it will always end up higher. All right, so a couple things to make sure you're cool with, that the exponential function in this form, and making sure you know what those components look like. Make sure you know why a graph would be exponential or linear, and what those graphs would look like in comparison to each other. All right, so linear versus exponential. And we'll meet up in class and see what we can do with all this. All right, here we go. See you soon.